LearningMeasure.tv, science and engineering podcast with emphasis on measurement. Brought to you by David Archer and LearningMeasure.com. Episode 17, Antenna Arrays. Hello, I'm David Archer, owner of LearningMeasure.com and LearningMeasure.tv. This podcast is sponsored by TradePub.com, GoToMeeting.com, and is part of the Blueberry community of podcasts. First of all, LearningMeasure.com is a subscription-based training website for engineers and scientists and technicians, or just people who have technical interests. It's free to explore for 2 weeks, and then it's $5 a month after that for a subscription in order to help pay for course development, this podcast, and that sort of thing. Okay, the topic of this podcast is antenna arrays. This is a continuation of last time's podcast on the isotropic radiator. From the numbers, it looks like maybe you guys aren't interested in this so much, but I'll make this the last of this series. I really want you guys to start giving me suggestions on what to do next, because I know some of you, there are people watching this podcast. I only get a very little bit of feedback. So, okay. Last week we saw when you had two isotropic radiators, as you moved them apart in space, first of all the main lobe got narrower and narrower, the main beam. But also, as they got further apart, other lobe structure started appearing in the pattern. This time we're going to look a little bit at what happens when you have more than two. We're going to look at a linear array of, well, in the case of the example, we're going to give a linear array of 10 elements. But before we get into that, do a pay the bills a little early this time. If you're looking for a better way to present or collaborate during your conference calls, your solution is simple. Web conferencing with GoToMeeting. During your call, everyone logs on to GoToMeeting.com and your computer screen shows up on their computer screens. It's like you're in the same room. GoToMeeting is perfect for sales or product demos, training or real-time collaboration, plus you're not charged per minute like other providers. You can meet as often as you want for as long as you need. With GoToMeeting, you can meet with anyone, anywhere, without ever leaving your office. You'll not only save time, but money too. See for yourself. Try GoToMeeting free for 45 days. Just visit gotomeeting.com/podcast. That's gotomeeting.com/podcast. What we're going to do now is we're going to look at what happens when you have a larger array of radiators with another Excel spreadsheet. Okay, that's what we'll do next. Well, here's a modification of the spreadsheet you saw last week. What we've got here now is we've got two, you see this is a linear display here of a plot of the pattern, and over here we've added a logarithmic display. This is in dB. Right now, the only difference, well, the main difference is now you can put in any number of isotropic radiators. Right now it's set to 2, and again, as you change the spacing, you see exactly the same as you did last time, except you can see some of the, because of the logarithmic scale here, you can see some of the structure that's starting to form here, even though you can't see it all that well here. So it looks pretty much like it did before. You get out to the main beam gets narrow and more structure starts to appear as you spread them apart. Okay, now we'll go back to 0 spacing, so they're all right on top of each other. And let's change this to the 10 now, 10 isotropic radiators. And that's going to look a little bit different as you increase the spacing. Still you form a nice beam, but then it just gets narrower and narrower as the spacing goes. And you can see, you can't see it so much here, even though there's more structure appearing. You can see right there, I can hardly see anything, but here in this dB scale you can see there's a lot more structure. But notice it's a lot farther down in magnitude. As you increase the spacing, at some point though, you notice that it's getting narrower and narrower, more and more structure appears. But then all of a sudden a big side lobe appears. Also, it's called a grading lobe. It's kind of a replica of the main lobe. It's just because the elements are spaced too far apart for these not to appear. And as you have the spacing get further and further apart, again more structure appears, and then eventually another large lobe appears. The main lobes here still are getting narrower and narrower, while these other lobes keep appearing. Now this spreadsheet will be available on the show notes at learningmeasure.tv, so you can play with the spreadsheet and do what you want with it, just to learn what's going on. That's it for now. See you in a minute. Okay, now that we've shown you what happens with an array and how they move, what happens when you move them apart, we're going to talk a little bit more about beam steering. As you noticed when with last week when we did the two elements, that if you change the relative phase between the two elements of the array, the two isotropic radiators, the beam sort of steered up and down. Well, we're going to discuss how that works. Let's say you have an array of isotropic receivers, let's say, or radiators. It doesn't matter. You can do the argument either way. Now let's say you have some plane wave front coming in, which you've got a plane wave moving in this direction. And you want to know what's the phase of all the elements in the array. Let's say the position here is, well, we'll call this R1, R2. Well, we know that a form of a plane wave, we've already seen that from previous episodes, is e to the I k dot r. Okay. So obviously the phase at each one of these points is k dot r. Like here, the phase is k dot r1. And here it's k dot r2. You may have seen another derivation where if the phase here is, let's say, arbitrarily, you call this one here 0, and the wave's propagating this way. And if you look, you call this angle here theta. You can see that this distance here, since these are, the phase is kr this way, this spacing is d. This phase distance here is kd sine theta. It's exactly the same. It's exactly the same derivation. So if you arrange for the phase, let's say they're evenly spaced at with spacing d, then if the phase at each element is kd sine theta, or the phase at each element, same thing, is k dot ri. Okay, when that happens, that's what happens when what the phase is at each one of these points for an incoming plane wave. If these are receivers and you shift all the phases by that amount and then add them up, you get, they add in phase, right? Because they all have the same phase if you shift each one by that amount. So this one is at phi 1, whatever phase it is. This one's going to be at phi 1 plus kd sine theta. And this phi 2 is going to be phi 1 plus 2 times kd sine theta, if they're evenly spaced, etc. So if you subtract this amount from each of the elements by shifting the phase, they're all going to be the same phase, and they're going to add in phase, and you're going to get a gain. You're going to get a gain over by the number of elements. So the received power, if this is going to be something like, you know, well, it's going to be n squared type thing, but because the field combined is going to be something like n, once you do all these phase shifts, n times, well, let's see, the E incident on 1. So since power is proportional to the electric field squared, it's going to be n squared, power gain. Okay. Similarly, if you were trying to transmit from each one of these and you adjusted the phase in this manner or in this manner, it's the same thing. This was what you'd use if they weren't in a line and they weren't evenly spaced. You would get the boundary conditions for a plane wave actually in that plane. So you would radiate out in the direction by k. Now, what is this k for steering? This k dot ri, for more arbitrary, let's say you have a bunch of radiators like this. You know, they're just all over the place or some sort of thing. And you want to create some sort of, maybe they're on some weird surface, and you want to create a beam. Well, k is going to be, well, 2 pi over lambda times cosine, these are all polar coordinates. Let's erase some of this stuff. Cosine theta, sine theta, cosine phi, x hat plus cosine theta, cosine phi, sine phi, y hat plus sine theta z hat. So if you had something at position x hat r xi, let's say, for each element, plus y hat plus z hat. If you wanted a plane wave with a certain this value of k, all you would have to do on these elements is you have to set the phase at each element is k dot r, right? So it's 2 pi over lambda times xi cosine phi sine theta, etc., plus yi sine phi sine theta plus zi cosine theta. Okay. So once you have an array of isotropic radiators with this phase, where it's a linear array or whatever, you can create, and you excite them with this phase, equal amplitude, you will create something like a plane wave within that direction. Okay. Now there's limitations to that. We'll not get into that here. First we're going to pay another bill. All right, we'll be back right after this.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories, and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Now we're going to play around with this spreadsheet again and show you what happens as you tweak the phase of a linear array of isotropic radiators.
Okay, here we are with that spreadsheet again. And what we're looking at now is a 50 element linear array. Set it up for basically something like a half wavelength spacing. Well, actually less than that. And as you can see, it's a nice narrow beam. Now what we're going to do is add a KD sine theta phase shift to progressive phase shift to each element and see what happens. So as you move change the phase, change the angle in KD sine theta, the thing moves up. There's at 30 degrees, it looks like 30 degrees. Put it up to 45 degrees, looks like 45 degrees, and as you can see in the logarithmic plot, there's a lot more structure showing up down here. Okay, I'll keep steering it up. It goes up to 50 degrees. It still looks pretty good. But now whoops, let's go down a little. When you get up a little high, you start to see the lobes filling in between the thing, and as you approach 90 degrees, which would be an end fire configuration, you end up with a single lobe. Okay, and you can see, if you look, there's one single lobe, but there's no lobe down here in the bottom half. That's different from the two element case. And if you notice, if I change this to 2, there would be one going up and one going down. So at 90 degrees, as more elements are put into the array, one side of that in the end fire configuration disappears. And if I go to the other extreme, you see that it does the same thing symmetrically. And so this is an effective way of steering a beam. Now this is for a linear array. If you want to use a planar array or some other type of geometry, you can steer it in more than one dimension. And with a linear array, you're only going to steer in one. This spreadsheet will be available for download on the show notes. You can play around with it and see what happens as you change the various things. Like here, if we open up the spacing a bit so that there's a grading lobe that appears. Let's see, there's one. The beam still steers, but it also steers the grading lobes. And at some point you're not sure what the main beam is anymore. But so it's important for these things in general that the spacing's kept small. Okay, well that's it for this.
Okay, now that I've shown you that, I wanted to go over a few examples of antenna arrays and what you might use them for. Okay, this is an image here of the National Radio Astronomy's very large array, or also known as the VLA, radio telescope in Socorro, New Mexico. The VLA consists of 27 dishes mounted on tracks, and the so the spacing of the antennas or the array elements can be moved in and out. Each antenna is 25 meters in diameter. So what happens is, you wonder why are they not at a fixed spacing? Well, as you see, as you move the elements apart, the beam gets narrower and narrower. You also have the problem of more lobe structure. But the advantage of moving them apart is you get a very narrow beam. So your resolution goes up, but there's a cost associated with that. As you move the antennas further and further apart, the patch of sky you are looking at gets smaller and smaller. So if you wanted to look at a big patch of the sky, you have to be scanning that beam for a long time to cover that, to image that part of the sky. So if you want to do a large part of the sky, like some sort of survey, or you're going to, image a close by galaxy or maybe even try to image the moon or something that's angularly large, if you're in this largest configuration, it's going to take you a lot longer to do it. So sometimes you want to move your antennas closer together. You get a less resolution, you get a larger beam, but it takes less time to survey the sky because you're looking at bigger chunks of it at one time. So there's all kinds of reasons. There are other reasons why you might want to move the antennas apart. But that's basically it. What can you do with this? Well, at the highest resolutions, you can do things like this image here, which is a radio image of the M33 galaxy. If you look at this false color on this image, it's showing Doppler shift. So this is a direct measure of the rotation of this galaxy. The red areas are moving towards you and the blue areas are moving away. They can know what the frequency is from basically atomic theory. They know what the energy of a particular transition they're looking at would be. Therefore, they know the wavelength. Therefore, they can look at the Doppler shift and determine the rotation rate of the galaxy. This is a direct measure of the rotation rate of the galaxy using radio waves. Okay, the next thing to look at, if you want to do even more resolution, baselines the size of what you can get in the VLA is too small. And they have something called the VLBA, Very Large Baseline Array. This is a picture of where the locations are. And it's 10 telescopes with a baseline that's probably it's about 5,000 miles wide. Again, it gets you better angular resolution on the sky, so it might be looking for very distant sources, trying to get some resolution on a very distant source. You need a larger antenna. Obviously, the next place to go if you want things bigger is to put a series of radio telescopes in space and somehow connect them together and process the data so you have a very large antenna made up of antenna elements that you could even get more resolution for. And you could do this optically as well, because it's just another band in the spectrum. Another example of antenna array is like phased array radar. Here's an example of something that's called pave-pause radar. It's found in Alaska. Very big radar, lots of elements, thousands of elements. Can scan the sky electronically, quickly looking for things. But obviously the applications of this is not just electromagnetic. You can have arrays in sonar or ultrasound. You could have detector arrays in, just for any other type of radiation you can think of. Although that's a little bit different. You generally don't use phase and things like, but you still can generate, you can get directions. But that'll be it for this week. We're not going to do another antenna episode next week, or next time, whatever time we do it. Please, we need your suggestions. Send us your questions. If you have any question at all, homework question, engineering question, I don't know, personal questions, although it's no guarantee that you'll get it answered, send your questions to questions@learningmeasure.tv. If you have a suggestion for a topic you'd like to see covered, send it to suggestions@learningmeasure.tv. And if you're a vendor that would like to demo your products, or you are interested in, you're a consultant and you want to sell your services and you want to be on the podcast and you're in the Las Vegas area, send us an email at vendors@learningmeasure.tv and we'll try to get you on the show. Okay, that's it for this episode. We'll talk to you next time.